In past videos, we discussed probability density functions for a single variable. But in econometrics, we're interested in the relationships that exist among variables. To analyze those, we need to talk about joint probability density functions. A joint probability density function tells us the probability that a given set of variables will take on specific values. In the general case, if we have n random variables, x1 through xn, the joint probability density function tells us the probability of observing any given combination of each of those variables. There are two properties with this which are very similar to those we've seen for univariate probability density functions. Specifically, the probability of observing any combination of those random variables will always be between 0 and 1. And again, if it's 0, it means the outcome is never observed. If it's 1, it's a trivial case where the outcome is observed with certainty. The other characteristic is that the sum of the probability over all possible combinations of outcomes must add up to 1. In the case of a bivariate probability density function, where we have two variables, x and y, we can write that as the joint probability of observing each possible combination of x and y add up to 1, where we're doing a double summation there. In the inner part of that summation, we're holding the outer part constant, and we're adding up the probability for a given level of xi, all the possible outcomes for yj. In the outer part of that, we repeat that process for each possible level of xi. If you think of the joint probability density function as being represented by a matrix of probabilities, we're adding up all the elements in each particular row and column of that matrix. For example, suppose we take the joint probability density function that describes the relationship between education and income in a given population. We break up education into 4 categories: people who have not completed high school, people who have a high school degree as the highest level of education, people who have completed 1 to 3 years of college, and people who have 4 or more years of college. We break up income groups into 3 categories: low, medium, and high. With this, we can observe the probability of any combination of income and education in this population. For example, 8% of the population has both a low income and did not graduate high school. 1% of the population did not complete high school but has a medium income. 1% of the population did not complete high school but has a high income. And similarly as we go down each row. Now notice that the 2 characteristics of a joint probability density function are satisfied here. Each probability is between 0 and 1, and if we add all of these up, the sum of them comes to 1. If you're not sure about that, you can just add up those numbers and it should equal 1. For every joint probability density function, we can define marginal distribution functions. And the marginal distribution corresponds to the distribution for each of the variables without regard to the level of the other variables. So a marginal distribution involves essentially separating out, in that last case, the probabilities of observing educational attainment or of observing income levels without regard to the other variable. So it's a univariate probability density function derived from that multivariate distribution. If we want to find the marginal distribution for the random variable x, we just take the sum of all the joint probabilities over all the possible values of y. So to find the probability that x equals x1, we look at all those combinations of x and y where x equals x1, and we add those up for all possible levels of y. Similarly, to find the probability that y equals yj, we add up all the probabilities of y equaling yj over all the possible levels of x from I equals 1 to n. Take a look at this table and see if you can compute the marginal probabilities for each level of educational attainment and for each level of income. If we want to measure, for example, the probability that someone has less than a high school degree, there are 3 groups of people that meet that criteria. and those are in the first row of this table. So 8% of the population has not completed high school with a low income, 1% has not completed high school but has a medium income, and 1% did not complete high school but has a high income. Essentially, 10% of this population did not complete high school. Similarly, of the people with a high school degree, if we look at the high school degree category, we observe that 10% of the population had high school degrees with a low income, 32% completed high school with a medium income, and 5% of the total population completed high school and ended up with a high income. So in total, what we're observing is that 10 plus 32 plus 5% of the population, or 47% of the population, have completed high school. And we can do that for each row of the table to find the probability of a random person in the population having any given level of educational attainment. Similarly, for income, we know that some low-income individuals did not complete high school. Some have a high school degree, some have 1 to 3 years of college, and some have 4 or more years of college. The total proportion of the population that has a low income would be just the sum of the elements in that column. So it would be 8% plus 10% plus 4% plus 2%, which is 24% of the population. And we can do the same thing to compute the marginal probability of observing someone with a medium income or a high income. If you do that for each of the rows and each of the columns, you'll see that the marginal distributions satisfy the conditions for a probability density function. In particular, the probability of each outcome is between 0 and 1, and the sum of those marginal probabilities add up to 1. That's a good way of checking that you did not make a mistake when you derive the marginal distributions.